Why does one mission to Jupiter move forward while another, equally brilliant, disappears before it leaves the page? It seems like a simple question, yet it opens a door into the quiet structure that decides the future of exploration. I think about this often because the images you see from distant worlds aren't just the result of engineering, they are the end of a long negotiation between science, politics, budgets, and timing. When I talk to people about space, many imagine that missions begin with a great idea and move naturally toward launch. But the truth is more complicated. A mission lives or dies based on the alignment of Congress, the White House, NASA's internal priorities, and the small window in which all of them agree. Even the most inspired concept can fail if any part of that alignment shifts. And when the alignment holds, you get Voyager, Cassini, Europa Clipper, projects that shape how we understand the universe. This is why I want to walk you through the hidden architecture of space exploration. Not the hardware, but the system that decides whether hardware ever exists. The committees that write NASA's instructions. The budgets that rise and fall with political tides. The advocates and scientists who spend years preparing the ground so a mission can take root. These forces shape the exploration you see today, and they will shape what we discover in the next decade. Most people imagine space exploration as a contest of engineering skill. Build the right rocket, design the right instrument, and the rest follows naturally. But before a single bolt is tightened, a mission must pass through something far less visible: the architecture of space policy. If you want to understand why a mission exists, why it is funded, or why it takes a decade to unfold, you have to look at the system that shapes NASA's decisions long before a spacecraft reaches a launch pad. I learned this early in my career after spending time in Washington, D.C. What struck me most was not the technology. It was how many people influence each step of a mission without ever touching the hardware. A spacecraft might carry the work of thousands of engineers, but it also carries the imprint of committees, appropriators, advisors, analysts, and voters who shaped its path. In space policy, nothing moves alone. The United States runs exploration through three major centers of power: the White House, Congress, and NASA itself. Each plays a different role. The White House sets broad priorities through agencies like the Office of Science and Technology Policy. Congress provides the actual money and writes the laws that NASA must follow. NASA turns those directives into concrete programs, choosing missions, refining timelines, and managing risk. When these three align, exploration accelerates. When they diverge, missions slow, stall, or disappear. This structure may sound abstract, but it has direct consequences. Consider the difference between authorization and appropriation. Authorization is permission, Congress telling NASA what it may pursue. Appropriation is the money, what NASA can actually do. You can authorize a mission to study an ocean world, but unless its budget appears in the appropriations bill, the mission remains nothing more than an idea. Many promising concepts never progress because they reach authorization without the funding to follow. NASA's internal system adds another layer: the Science Mission Directorate, Human Exploration and Operations Mission Directorate, Space Technology Mission Directorate, and Aeronautics all compete for slices of a finite budget. Each has its own scientific community, its own priorities, and its own rationale for why its work deserves attention. When NASA receives instructions from Congress, those directorates interpret them through their own lenses. The final outcome is rarely a perfect translation of the original intention. It is a negotiated middle ground shaped by dozens of competing needs. This structure is not accidental. It emerged over decades, shaped by historical pressures and lessons from earlier programs. NASA was born during the Cold War, when national prestige and geopolitical strategy drove rapid investment. That urgency built the Apollo program, but it also created a long-term challenge. Expectations for exploration became tied to political momentum. When administrations changed or priorities shifted, missions could be delayed or transformed. Over time, the system adapted, favoring stability and continuity over dramatic swings. This is why some major projects extend across multiple presidencies. They rely on bipartisan agreement rather than fleeting enthusiasm. Another element many people overlook is the role of the scientific community. Every 10 years, researchers work with the national academies to produce a decadal survey, a document that outlines the most important scientific questions for the next decade. These surveys guide NASA more than any individual speech or budget request. When a mission aligns with a decadal priority, it gains scientific legitimacy and political resilience. If it falls outside that framework, it faces a steeper path. The decadal process is slow, deliberate, and designed to outlast political turbulence. Yet even with these systems in place, a mission still requires something else: public support. I have seen congressional offices respond to a surprisingly small number of calls or letters from constituents. Space is not a polarized issue. Many representatives have no strong opinion until a voter gives them one. When people speak up, even modestly, it can shift the balance. That is why advocacy organizations exist, not to replace the public, but to make it easier for people to participate in the process. Understanding this policy structure changes how you interpret space exploration. When you see a new mission proposed, you can ask, does it match decadal priorities? Does Congress support it? Does it have funding in the appropriations bill? Is the technology ready? Are there committees championing it? Each question reveals a different layer of machinery behind the scenes. Space exploration is often portrayed as a quest for the unknown, but it also depends on predictability. Missions need consistency, stable funding, clear objectives, reliable timelines. Without those things, even the most brilliant concept remains grounded. Policy provides that stability. It may not be glamorous, but it is the quiet infrastructure that allows exploration to unfold. This is why I often describe space policy as the gravity of the exploration system. It shapes the trajectory of every mission. It creates boundaries, enables momentum, and determines what is feasible. And just like gravity, you don't have to see it directly to notice its effects. You feel them in every mission that launches, and every mission that never does. A space mission begins in a place far quieter than a launch pad. I often picture a small group of scientists sitting in a borrowed conference room, sketching early concepts on a whiteboard that still carries the remnants of a previous meeting. They are not thinking about rocket plumes or countdown clocks. They are thinking about gaps in our understanding, an unexplored terrain on an outer moon, a spectrum that hints at hidden chemistry, a crater field that doesn't behave the way models predict. That modest moment, usually unseen, often undocumented, is where a mission first takes form. In those early months, the ideas feel almost fragile. A mission concept is nothing more than a claim that a particular question is worth pursuing and that a spacecraft can be built to answer it. I've watched scientists refine these claims through countless discussions, each one carving away uncertainty. They outline which instruments could capture meaningful data and which technologies are mature enough to trust. They evaluate whether the deep space network can support the bandwidth they need, or whether a new antenna design must be developed from scratch. They even consider how solar radiation, orbital mechanics, or thermal conditions will influence the overall architecture. All of this happens before NASA formally acknowledged the mission's existence. NASA's life cycle is structured to absorb this long prelude. The agency's Phase A studies examine a mission's viability with care that can feel almost surgical. Teams produce clearer definitions of their objectives, test early design assumptions, and identify the most sensitive technical risks. I've read Phase A reports that devote dozens of pages to the geometry of a single antenna or the thermal gradients across a thin instrument panel. These details may seem small, yet they determine whether a spacecraft can operate after years of travel through cold, radiation, and vacuum. Behind every future image from another world there lies this level of scrutiny. Phase B adds a different kind of weight. A mission must transition from possibility to commitment. Engineers refine mass estimates, model power consumption, and project thermal loads across an entire orbit. Scientists translate broad goals into specific observational strategies. Budget analysts construct multi-year cost curves, mapping out how money will be spent and how delays might ripple outward. NASA's standing review boards, groups of independent experts, study these documents line by line, pushing teams to defend their assumptions. I've sat through several of these reviews. The atmosphere feels exacting, but never hostile. Everyone in the room understands that a flaw left unresolved in Phase B could undermine the mission many years later. Technical readiness plays a decisive role here. NASA maintains a scale known as TRL, Technology Readiness Level, to evaluate whether instruments or components are mature enough for deployment. A concept that relies on a TRL level too low may be postponed until the technology progresses, or it may be redesigned entirely. Some of the most elegant mission ideas never advance because a single key instrument cannot operate reliably in the expected conditions. It's a reminder that space is unforgiving, and marginal technologies rarely survive the climb from paper to hardware. The Government Accountability Office adds its own form of oversight. GAO publishes annual assessments of NASA's major projects, tracking cost growth, schedule shifts, and risks that require mitigation. These reports influence congressional expectations and shape public understanding of how missions evolve. Although GAO's presence may feel like pressure, it reinforces a principle that underpins the entire process. Transparency produces resilience. A mission that can withstand repeated external reviews tends to survive the political fluctuations that occur throughout its development. A mission's scientific value must also align with community priorities. The decadal surveys produced by the national academies provide the backbone of NASA's science planning. These documents emerge from extensive analysis, public workshops, and evaluation of scientific opportunity. A proposed mission that addresses a top priority question gains a level of legitimacy that no single researcher or institution could generate alone. I find this system reassuring. It ensures that NASA's long-term science program remains focused on the most meaningful questions rather than whichever ideas happen to be fashionable at a given moment. Outside the formal pipeline, an ecosystem of pre-phase and low-A studies pushes exploration forward. NASA funds instrument prototypes, laboratory experiments, and mission architecture models. Universities collaborate with industry partners to identify novel propulsion concepts or more efficient detectors. International agencies evaluate possible contributions. Each study may be small on its own, but collectively they create the intellectual environment in which major missions take shape. Even when specific proposals are not selected, their components reappear years later, refined, reconfigured, or supporting an entirely different mission. A mission that reaches Phase C begins to feel tangible. Hardware emerges slowly from drawings and simulations. Metal is machined. Detectors undergo calibration in vacuum chambers. Solar arrays are tested for microcracks. I've walked through clean rooms where spacecraft structures sit quietly beneath bright lighting, covered in protective sheeting. Even in that near-silent environment, you can sense the scale of what's unfolding. Every bolt, every circuit trace, every seam has passed through years of paperwork, reviews, and analysis to reach that room. What fascinates me most is how long a mission exists before the public even hears its name. Europa Clipper is a perfect example. Long before it became a visible program, scientists studied Jupiter's radiation belts, tested shielding materials, calculated gravitational assists, and mapped out candidate trajectories. Policy teams analyzed budget cycles to identify windows where stable funding might exist. Congressional supporters inserted language into appropriations bills that kept Europa exploration on NASA's agenda. When the mission finally entered development, the groundwork had already been laid by an entire decade of quiet progress. This early history shapes the entire lifespan of a mission. It determines which technologies are used, which scientific questions are emphasized, and which international partners join. It defines the mission's resilience and the likelihood that it will reach the launch pad. Spacecraft succeed because these invisible structures guide them long before engines ignite. Planetary science does not move at a steady pace. It expands, contracts, endures shocks, and regains momentum in ways that feel almost rhythmic. I've watched these cycles unfold closely, and each one reveals how fragile exploration can be when budgets shift and political focus wavers. Understanding this pattern helps explain why the field looks the way it does today, and why so many researchers remain cautious even in periods of growth. During the early 2000s, planetary science held a comfortable position within NASA. Flagship missions like Cassini were operating in full stride, Mars exploration was thriving, and the discovery era of smaller missions, such as Dawn and New Horizons, had begun to reshape expectations for what compact spacecraft could achieve. Beneath that activity, however, a structural weakness lingered. Budgets did not grow in proportion to the ambitions of the scientific community. Inflation gradually eroded spending power, and several major missions approached costly phases simultaneously. A tight system became tighter each year. The pressure became unavoidable around the early 2010s. NASA's proposed budgets for planetary science dropped sharply. I remember reading the Michilo presidential request one year and seeing numbers that felt incompatible with the program's ongoing commitments. Several missions under consideration, including a potential Europa project, appeared increasingly at risk. Laboratory funding thinned. Technology's development slowed. Younger scientists questioned whether the field would remain viable for the next generation. It was an unsettling moment, and not just for researchers. Policy advocates felt it too, because a cut of that scale ripples outward for a decade. The recovery began through sustained effort, advocacy groups, professional societies, and individual scientists work together to highlight the long-term consequences of deep reductions. Their messaging resonated because planetary science delivers clear results: landers on Mars, flybys of icy moons, high-resolution maps of asteroids, and atmospheric measurements that improve our models of early Earth. Members of Congress responded. Instead of accepting the proposed reductions, they increased planetary funding above the presidential request, at first by modest increments, then by amounts large enough to shift the trajectory of the entire program. That change restored momentum. Planetary budgets rose by hundreds of millions of dollars beyond initial proposals, and the trend continued for several years. These increases did not erase the earlier cuts instantly, but they created a foundation on which new missions could be built. Programs like Discovery and New Frontiers began selecting fresh targets. Missions to small bodies such as Psyche and Lucy moved forward. Technology investments strengthened, particularly in radioisotope power systems and advanced detectors. The field regained confidence. A key reason for this rebound lies in NASA's approach to scientific priority setting. The Planetary Decadal Survey identifies the most compelling questions every 10 years, providing Congress with a stable reference point. When lawmakers see consistent recommendations across different administrations, it becomes easier to justify support. That stability helps insulate science from political turbulence. Even in years when budgets face downward pressure, the Decadal Survey provides a roadmap that encourages continuity. The Europa Clipper mission illustrates how these forces converge. Europa rose to prominence not because of a sudden surge of interest, but through decades of accumulated evidence: magnetic field measurements from Galileo, images hinting at active geology, and theoretical models pointing toward a subsurface ocean. Each layer of research strengthened the scientific case. When budget conditions improved, the mission occupied a ready position. Scientists had refined instruments, policy teams had framed its importance, advocates had built support among legislators. A single fiscal year increase could activate the entire chain. Cycles in planetary science are influenced by more than funding. They also reflect the aging of long-running missions. When a mission like Cassini ends, a scientific gap forms, data stops flowing. Early career researchers lose a stream of material that might have shaped their careers. If a successor mission has not been prepared years in advance, entire subfields can experience a lull. This is why regular mission cadence matters so much. It sustains both research output and professional stability. The health of planetary science also depends on technology maturity. Many of the field's breakthroughs emerge from instruments that took years to evolve. Spectrometers designed to detect faint organic signatures, cameras capable of imaging through dense atmospheres, or radars that can probe beneath icy crusts. When technology development stalls, the next generation of missions inherits limitations from the previous one. The periods of budget recovery in the mid-2000s and late 2010s helped rebuild this foundation, enabling more ambitious mission proposals today. Another dimension of the cycle involves international collaboration. Agencies like the European Space Agency, the Japan Aerospace Exploration Agency, and the Canadian Space Agency each contribute unique capabilities. During periods when NASA's budget contracts, international partnerships can sustain scientific progress by sharing costs and expertise. During periods of growth, those same partnerships allow missions to expand their scope. The synergy strengthens the global explorations ecosystem, reducing vulnerability to isolated downturns. Despite these positive developments, the field remains mindful of past instability. Researchers track budget proposals carefully. Advocacy organizations continue to emphasize steady support rather than volatile surges. NASA invests in balanced mission classes: small discovery missions, mid-scale New Frontiers missions, and large flagships, so no single project dominates the program for too long. This balance spreads risk and keeps scientific diversity alive. From my perspective, planetary science today sits in a state of cautious optimism. Missions are in development across multiple fronts: ocean worlds, metallic asteroids, Trojan clusters, Mars sample return, and advanced lunar reconnaissance. The program is healthier than it was a decade ago, yet it carries the memory of how quickly conditions can shift. That memory motivates deliberate planning. It also reinforces the value of public engagement, because well-informed citizens help prevent severe disruptions from taking root again. Planetary science thrives when it maintains a steady cadence of missions, invests in technology, and builds community consensus. Those ingredients allow exploration to weather political cycles and budget variability. Understanding this dynamic makes the present moment easier to appreciate. The images arriving from distant worlds today are the product not only of innovation, but also of collective stewardship across many years. Some of the missions that survived the extreme budget storms of the early 2010s now point us towards some of the most intriguing places in the solar system. When I look at the next decade of planetary exploration, I see a pattern that has been building quietly for years. A shift toward worlds that preserve ancient chemistry, hide internal oceans, or record the earliest chapters of planetary formation. The spacecraft heading to these worlds do more than gather data. They test what a sustainable planetary program looks like. Europa remains one of the strongest examples of this shift. The idea that a moon orbiting Jupiter could host a global ocean first emerged from Galileo mission data in the 1990s. Tiny variations in the magnetic field hinted at a conductive layer beneath the ice, something deep, salty, and mobile. Over the following decades, improved models and laboratory studies strengthened the case. Europa moved from speculative curiosity to a priority for astrobiology. Today, Europa Clipper stands as the most capable mission ever constructed to examine an icy world. Clipper will not orbit Europa directly. The radiation environment near Jupiter is too harsh for long-term operations. Instead, the spacecraft will orbit Jupiter and dive past Europa dozens of times, each pass collecting new slices of information. Its instruments form a coordinated toolkit, an ice-penetrating radar to map subsurface layers, spectrometers to detect salts, organics, and potential plume materials, high-resolution cameras to examine fractures and chaos terrains. By stitching these flybys together, scientists can construct a three-dimensional picture of the moon's shell and infer the structure of the ocean below. No single measurement answers the habitability question. The answers emerge from accumulation, comparison, and patience. Asteroids provide a different type of insight. Psyche, the target of NASA's metallic asteroid mission, may represent the exposed core of an early protoplanet. If that interpretation is correct, the object offers a view normally locked away beneath hundreds of kilometers of mantle and crust. Studying Psyche means studying the earliest stages of planetary differentiation, how heat, pressure, and time turn raw material into layered worlds. The spacecraft approaching this body relies on solar electric propulsion, a technology that produces a constant, gentle thrust instead of a single explosive burn. That slow, steady push reflects a truth about modern exploration. Efficiency often matters more than brute force. Lucy, another mission shaped by the policy revival of the past decade, heads toward the Trojan asteroids that share Jupiter's orbit. These bodies are not a single population. They differ in color, composition, and possible origin. Some may have formed near the outer edges of the solar system. Others may have come from regions closer to the Sun. Together they act as time capsules from the system's chaotic youth. Lucy will perform multiple flybys, revealing how diverse these early remnants really are. Each visit offers a glimpse into processes that shaped every major body we study today. While these missions travel toward distant targets, an equally ambitious sequence is forming closer to home: the effort to return samples from Mars. The Perseverance rover, which landed in 2021, represents the first phase of this architecture. It drills, collects cores, and stores them in titanium tubes on the Martian surface. Later missions, planned jointly by NASA and ESA, will collect those tubes, launch them into Mars orbit, and transfer them to a return spacecraft bound for Earth. Nothing like this has been attempted before. Launching a small rocket from another planet demands precise choreography. Power systems, thermal protection, and communications all must work on timelines measured in minutes, with no real-time input from Earth. The best evidence we have suggests that this architecture is feasible, but the margin for error is narrow. Energy is one of the constraints linking many of these missions. Solar power becomes weak in the outer solar system, and thick shadows on icy moons limit panel efficiency even near Jupiter. Radioisotope power systems fill that gap. Their heat, produced by the decay of plutonium-238, drives thermoelectric converters and keeps critical components above freezing. For years, the United States had limited supplies of this material, relying on stockpiles left from the Cold War. In the 2010s, the Department of Energy restarted production. This renewed supply made Europa Clipper's thermal design more flexible and allowed NASA to consider missions that would otherwise remain theoretical. Without stable power, entire categories of exploration, Enceladus landers, Titan rotorcraft, deep solar system orbiters would not be practical. Each spacecraft in this new generation reflects the long arc of preparation behind it. Engineers refine instruments over many years, often developing them for missions that are still only sketches. Policy decisions made early in a decade influence whether those instruments find a home. A single telescope concept that slips behind schedule or overruns its budget can unintentionally create gaps across the entire planetary program. When that happens, missions like Lucy or Psyche become buffers that keep the cadence of exploration intact. They provide the continuity needed for the next flagship to form. There's a quieter dimension to all of this. Every spacecraft heading outward carries the collective memory of missions that came before. Teams borrow insights from Galileo, Cassini, and Dawn and New Horizons. Navigation strategies evolve. Radiation models improve. Power systems become more efficient. The lessons accumulate across agencies and decades. What looks like a bold leap from the outside is usually the slow, upward climb of many incremental decisions. When I look at the next decade of robotic exploration, I see a set of machines heading toward places that would have sounded almost mythical a generation ago. A dark ocean under Europa's ice, a world made largely of metal, swarms of ancient rocks sharing an orbit with Jupiter, and a cache of rocks waiting on Mars to be brought home. Each of these targets carries a different piece of the story of how planets form, how they evolve, and how life might arise. Each one also exists only because a fragile line of policy and funding held together long enough for engineers to finish their work. Europa is a good place to start. The idea that this moon of Jupiter hides a global ocean beneath tens of kilometers of ice grew out of data from NASA's Galileo spacecraft in the 1990s. Tiny wiggles in Jupiter's magnetic field, measured as the moon passed through it, behaved as if an electrically conductive layer was being stirred deep below the surface. Salt water can do that. Later, images of cracked, jumbled ice suggested something warm and mobile pushing from beneath. When I picture Europa now, I do not picture a smooth white marble. I picture a thick, cold shell floating on a dark, restless sea, lit only by faint starlight filtering through the ice. Europa Clipper is designed to approach that world with a kind of patient precision. Instead of parking in orbit around Europa, where Jupiter's radiation would quickly damage electronics, it will loop around Jupiter and swing past the moon again and again, building up coverage. I think of it as a survey plane flying repeated passes over the same coastline. An ice-penetrating radar will send radio pulses into the crust and listen for echoes, tracing layers and possible channels of liquid water. Infrared and ultraviolet spectrometers will search for salts and organic molecules at the surface. Cameras will look for fresh scars, plumes, and places where the ocean might come closest to the exterior. No single instrument is sufficient on its own. The power comes from overlapping maps built flyby to flyby, until Europa is no longer just an icy dot, but a complex layered object with specific places we might want to land someday. Asteroids offer a very different kind of story. Psyche, the target of NASA's Psyche mission, may be the exposed metallic core of an early protoplanet. If that interpretation holds, it is as if the solar system has left a cutaway model out in deep space. Most of the time, planetary cores are locked away beneath thousands of kilometers of rock and mantle. Here, the dense interior may sit relatively close to the surface. Radar observations from Earth already suggest a high metal content. As the spacecraft closes in, it will map the gravity field, surface composition, and texture. I tend to imagine Psyche as a scarred, dark world with cliffs and craters carved into nickel-iron rock, maybe mixed with silicates, the remnant of violent collisions in the early solar system. Studying it is a way to test ideas about how heat, radioactivity, and repeated impact separated metal from rock when planets were still young. The Psyche spacecraft itself uses solar electric propulsion, a technology that trades raw thrust for long-term efficiency. Xenon gas is ionized and pushed out the back of the engine in a smooth, continuous stream. To me, the mental image is more like a slow tugboat than a firework. The acceleration at any given moment is gentle, but sustained over months and years. The cumulative effect bends the trajectory in ways chemical rockets cannot easily match. Missions like NASA's Dawn, which orbited both Vesta and Ceres, demonstrated how powerful that approach can be for touring multiple bodies without enormous fuel loads. Lucy, another mission shaped by decisions from the last decadal survey and budget turnarounds, heads toward the Trojan asteroids that share Jupiter's orbit. These objects cluster around two stable regions, leading and trailing the planet. They are thought to be remnants from different parts of the solar system, trapped early on by the giant planet's gravity. When I think about Lucy's path, I picture a long, looping trek that threads through these swarms, each flyby adding another piece to a growing collage. Differences in color, density, and surface composition will tell us whether these bodies formed in the cold outer regions near the giant planets or somewhere in between. In that sense, Lucy is less a single mission and more a moving observatory tracing out the diversity of leftover building blocks. While those spacecraft set off toward distant targets, an equally ambitious chain of events is forming around Mars. The Perseverance rover, which landed in Jezero crater in the year 2021, is the first step of a Mars sample return campaign. It is quietly drilling cores, sealing them in metal tubes, and placing them in carefully chosen spots on the surface. Future missions planned by NASA and the European Space Agency will land near those depots, collect the tubes, and load them into a small rocket. That rocket will launch from Mars, rendezvous with an orbiter, and then send the samples on a return trip to Earth. From a policy perspective, I see this as a long, interlocking contract with the future. No single mission can accomplish the goal. It takes a sequence sustained across multiple presidential terms and budget cycles. The technical challenge is equally striking. Launching from another planet means designing a vehicle that can sit for months in the Martian environment, start reliably, and execute a sequence with no real-time human intervention. The communications delay makes it impossible to adjust in the moment. The ascent stage has to work the first time. If it does, the reward is extraordinary. Small rock cores from a dried-up river delta on Mars could eventually sit in Earth laboratories, under instruments far more capable than anything we can send on a rover. That is the trade the system is making. Decades of planning in the nodes, exchange for a few kilograms of carefully chosen material. All of these missions depend on reliable power. Far from the sun, solar panels produce very little electricity. In permanently shadowed regions or under thick atmospheres, sunlight may not be practical at all. Radioisotope power systems step in here. They use the steady heat from the decay of plutonium-238 to warm instruments and generate electricity through thermoelectric devices. For a long time, the United States had only a modest remaining stockpile of this material, left over from Cold War production. In the last decade, the Department of Energy restarted manufacturing in small but steady quantities. That quiet decision in a non-space agency opened the door for missions like the Dragonfly rotorcraft to Titan and gave designers more options for Europa and outer solar system concepts. When I think about these spacecraft, I often picture a compact, warm heart of metal, keeping delicate electronics alive while the outside world sits at temperatures hundreds of degrees below freezing. Taken together, Europa Clipper, Psyche, Lucy, and the early stages of Mars sample return represent more than isolated projects. They form a pattern of exploration that spreads risk, uses a mix of mission sizes, and builds on decades of technical heritage. They are only possible because planetary science funding recovered after its near collapse, and because decadal priorities were taken seriously by both NASA and Congress. The visible hardware is the outer shell. Inside that shell are years of meetings, reviews, and budget lines written in careful legal language. To see the pattern clearly, it helps to step back and look at one of the most debated pieces of hardware in the current program, the heavy lift rocket that has dominated so many conversations about cost and direction. Understanding how that vehicle came to be and what role it plays means stepping deeper into the political physics of spaceflight. The space launch system often appears in conversations as a symbol of inefficiency, as if it were built solely to anchor debate threads online. When I look at it through the lens of policy, I see something different. I see a rocket whose existence is rooted not in pure engineering logic, but in the gravitational pull of law, industry, and political structure. SLS is, in many ways, the clearest example of how American space policy operates when technical goals intersect with congressional priorities. The rocket emerged from a moment of transition after the retirement of the space shuttle. When shuttle flights ended, thousands of workers with decades of expertise stood at risk of dispersing. Facilities in Florida, Alabama, Louisiana, and Texas were in danger of falling silent. In 2010, Congress responded through the NASA Authorization Act, which directed NASA, by law, to develop a heavy lift vehicle using shuttle-derived hardware and workforce. That sentence in the statute sealed SLS into existence long before a single piece of hardware reached a test stand. To understand why, imagine the industrial geography of the American space program. In Alabama, the Marshall Space Flight Center houses propulsion development. In Louisiana, Michoud manufactures large tanks and structures. In Florida, Kennedy Space Center launches the rockets that carry them skyward. Each location represents jobs, contracts, and decades of accumulated capability. Representatives from these regions do what elected officials are expected to do: preserve economic stability at home. From their perspective, SLS is not just a rocket. It is an anchor holding a network of skilled workers in place. That doesn't mean SLS has no strategic purpose. Congress deliberately framed it as a national asset, similar to how an aircraft carrier is sometimes justified, not purely by cost efficiency, but by maintaining sovereign capability. A heavy lift system owned directly by the government provides assurance that, even if commercial markets fluctuate or private companies shift priorities, the United States retains a guaranteed path for launching massive scientific missions or human exploration and hardware. Still, when you compare SLS to rapidly evolving commercial vehicles, the contrast is striking. SpaceX, Blue Origin, and United Launch Alliance all pursue reusable systems that reshape expectations for cost and cadence. But the distinction between them and SLS is not simply a matter of performance. It is structural. Commercial rockets answer to customers, markets, and investor expectations. SLS answers to Congress because Congress wrote it into law. NASA cannot cancel it without violating statutory requirements. That alone creates a completely different decision environment. I sometimes think of SLS as a form of political inertia made visible. Once a commitment like this enters law, it moves forward unless something stronger intervenes. You can see that inertia in the way SLS survived administration changes, budget reshuffles, and waves of criticism. None of those forces outweighed the deeper pull of congressional mandate. When people ask me whether NASA should rely entirely on commercial rockets, I remind them that NASA's goals exist within broader political constraints. The agency cannot simply choose the most cost-efficient option. It must navigate a landscape where stability, employment, legal instruction, and national identity all exert influence. SLS becomes understandable only when you step back and observe all of these forces acting at once. From a policy perspective, SLS is not an anomaly. It is one chapter in a long history of large national projects shaped by more than engineering metrics. The Saturn V emerged from Cold War strategy. The shuttle emerged from institutional compromise. SLS emerges from a desire to preserve technical capacity and distribute economic benefits while enabling deep space ambitions. As someone who works in space policy, I find that seeing SLS through this lens changes the tone of the conversation. Instead of treating it as a binary competition with commercial rockets, it becomes a reflection of competing priorities within a democratic system. You can disagree with the outcome, but the underlying logic remains consistent with how the United States often builds large, publicly funded infrastructure. At the same time, even the most carefully constructed political logic encounters resistance from technological change. Commercial heavy-lift vehicles are progressing quickly. Reusability is no longer experimental, it is routine. Market competition pushes prices downward and cadence upward. Over time, these factors may influence how Congress sees its options. Laws can change, though they rarely change quickly. As you and I follow the next decade of exploration, SLS will likely continue serving as a reminder that rockets are not only machines. They are political statements, employment engines, and strategic instruments. They solve engineering problems, but they also solve local economic ones. They reflect national identity as much as technological ambition. If anything, studying SLS helps illuminate a broader principle. Exploration is shaped by the structures that support it. Even the largest rockets trace their origins to decisions made quietly in committee rooms years earlier. The Space Launch System often appears in conversations as a symbol of inefficiency, as if it were built solely to anchor debate threads online. When I look at it through the lens of policy, I see something different. I see a rocket whose existence is rooted not in pure engineering logic, but in the gravitational pull of law, industry, and political structure. SLS is, in many ways, the clearest example of how American space policy operates when technical goals intersect with congressional priorities. The rocket emerged from a moment of transition after the retirement of the space shuttle. When shuttle flights ended, thousands of workers with decades of expertise stood at risk of dispersing. Facilities in Florida, Alabama, Louisiana, and Texas were in danger of falling silent. In 2010, Congress responded through the NASA Authorization Act, which directed NASA, by law, to develop a heavy lift vehicle using shuttle-derived hardware and workforce. That sentence in the statute sealed SLS into existence long before a single piece of hardware reached a test stand. To understand why, imagine the industrial geography of the American space program. In Alabama, the Marshall Space Flight Center houses propulsion development. In Louisiana, Michoud manufactures large tanks and structures. In Florida, Kennedy Space Center launches the rockets that carry them skyward. Each location represents jobs, contracts, and decades of accumulated capability. Representatives from these regions do what elected officials are expected to do: preserve economic stability at home. From their perspective, SLS is not just a rocket. It is an anchor holding a network of skilled workers in place. That doesn't mean SLS has no strategic purpose. Congress deliberately framed it as a national asset, similar to how an aircraft carrier is sometimes justified, not purely by cost efficiency, but by maintaining sovereign capability. A heavy lift system owned directly by the government provides assurance that, even if commercial markets fluctuate or private companies shift priorities, the United States retains a guaranteed path for launching massive scientific missions or human exploration hardware. Still, when you compare SLS to rapidly evolving commercial vehicles, the contrast is striking. SpaceX, Blue Origin, and United Launch Alliance all pursue reusable systems that reshape expectations for cost and cadence. But the distinction between them and SLS is not simply a matter of performance, it is structural. Commercial rockets answer to customers, markets, and investor expectations. SLS answers to Congress because Congress wrote it into law. NASA cannot cancel it without violating statutory requirements. That alone creates a completely different decision environment. There is also a human dimension worth acknowledging. Large programs such as SLS preserve expertise that cannot be rebuilt easily. Welders who know how to fabricate massive cryogenic tanks, technicians who understand the quirks of engine test stands, engineers with fluency in arcane propulsion systems. These are not interchangeable roles. If national capability in these areas evaporates, recreating it could take a generation. Many supporters of SLS argue from precisely this point. Continuity matters in fields where rare skills anchor future exploration. When people ask me whether NASA should rely entirely on commercial rockets, I remind them that NASA's goals exist within broader political constraints. The agency cannot simply choose the most cost-efficient option. It must navigate a landscape where stability, employment, legal instruction, and national identity all exert influence. SLS becomes understandable only when you step back and observe all of these forces acting at once. From a policy perspective, SLS is not an anomaly. It is one chapter in a long history of large national projects shaped by more than engineering metrics. The Saturn V emerged from Cold War strategy. The shuttle emerged from institutional compromise. SLS emerges from a desire to preserve technical capacity and distribute economic benefits, while enabling deep space ambitions. As someone who works in space policy, I find that seeing SLS through this lens changes the tone of the conversation. Instead of treating it as a binary competition with commercial rockets, it becomes a reflection of competing priorities within a democratic system. You could disagree with the outcome, but the underlying logic remains consistent with how the United States often builds large, publicly funded infrastructure. At the same time, even the most carefully constructed political logic acts while it encounters resistance from technological change. Commercial heavy lift vehicles are progressing quickly. Reusability is no longer experimental. It is routine. Market competition pushes prices downward and cadence upward. Over time, these factors may influence how Congress sees its options. Laws can change, though they rarely change quickly. As you and I follow the next decade of exploration, SLS will likely continue serving as a reminder that rockets are not only machines, they are political statements, employment engines, and strategic instruments. They solve engineering problems, but they also solve local economic ones. They reflect national identity as much as technological ambition. The Lunar Gateway is often introduced with a scale model or an elegant rendering, and those visuals can be misleading in their own quiet way. The images look sleek, polished, almost futuristic. What I see after years of following the policy trail is something different. A small, deliberate outpost designed to answer one question: whether humans can operate safely and sustainably beyond the thin protective bubble around the Earth. The Gateway is not a moon base. It is not a return to the giant space stations of Cold War ambitions. It is a compact habitat, roughly the size of a few connected rooms, placed in a special orbit around the Moon called a near-rectilinear halo orbit. Engineers describe the orbit by referencing complex gravitational mathematics. The United States formally embraced the idea in a presidential directive that set a clear sequence: return humans to the Moon, learn from that experience, and build toward eventual missions to Mars. NASA responded by shaping a program that integrated Orion, the Space Launch System, commercial landers, and a small cislunar station, the Gateway. But even with a strategic direction, nothing begins until Congress provides the appropriation. That's the part many people overlook. NASA cannot commit to long-term contracts without the yearly budget law, and early Gateway work moved slowly because it rested on studies and incremental funding rather than full program authority. When you place hardware so far from Earth, the environment changes dramatically compared to the International Space Station. At the ISS, astronauts can return home in a matter of hours. Rescue capabilities exist. Communication delays are tiny. In the region where Gateway will operate, the distance stretches everything. Radio messages take longer. Quick return is impossible. Solar storms deliver radiation doses that require shelters and careful planning. The best current evidence from decades of robotic missions tells us that deep space is an unforgiving place for both metal and biology. One reason Gateway matters is its position as a test platform. A small crew can learn how to manage life support systems with fewer safety nets. Engineers can evaluate new shielding concepts and monitor how materials degrade in sustained radiation. Navigation, power management, and communication architectures can be rehearsed for Mars-class missions, where delays and failures cannot be waved away by a quick retreat home. These are not glamorous steps, but they are necessary. A civilization cannot extend itself into deep space without practicing close to home first. The outpost also serves as a logistical node. Landers headed for the lunar surface can rendezvous with Gateway, exchanging crew and cargo. Science instruments can be staged, repaired, and redeployed more flexibly than if every asset had to be launched directly from Earth. International partners, such as the European Space Agency, Japan's JAXA, and the Canadian Space Agency, see Gateway as an entry point for long-duration collaboration similar to the ISS, but architected for deep space rather than low Earth orbit. Not everyone supports the plan. Some critics argue the Gateway is a detour, that it adds complexity to lunar operations rather than simplifying them. They point out that Apollo demonstrated the ability to go directly from Earth orbit to the lunar surface and back. Supporters counter with a different perspective. Apollo was an extraordinary surge, fueled by Cold War urgency and immense spending. Repeating that surge repeatedly is neither politically nor financially sustainable. In that view, Gateway represents a more incremental but more durable approach. It builds infrastructure step by step, matching technical progress to long-term budgets. I tend to think of Gateway as a rehearsal space. Before you take a performance to a larger venue, you work in a smaller room where mistakes cost less. You refine routines, adjust timing, test equipment. You learn how the rhythm feels when the stakes are low. In this analogy, low Earth orbit is the warm-up studio you already know by heart. Gateway is the intermediate stage. And anything beyond, Mars, asteroids, deep space habitats, is the grand hall waiting in the distance. There's another layer too, the psychological shift. Living even a few days beyond Earth orbit alters how crews think about time and distance. Earth shrinks into a sphere, not a horizon. Communication delays accumulate. The idea of home recedes just a little. These are subtle experiences, but they matter, because human spaceflight is not only about hardware. It's about how people adapt to isolation, latency, and risk. Gateway creates a controlled environment to study that adaptation. If you picture it slowly circling the Moon, you begin to see its real purpose. It is a small island positioned in a vast sea, built by a civilization attempting to push its presence outward carefully, deliberately. It is modest compared to the visions in science fiction, yet ambitious when measured against the realities of budgets, engineering constraints, and the unforgiving conditions of deep space. And from the policy perspective, Gateway symbolizes something rare: international, multi-year cooperation in a domain of extreme difficulty. Politics will ebb and flow, budgets will rise and fall. But the idea of a shared outpost beyond Earth in the coming decade remains one of the most concrete signals that humanity intends to learn how to operate away from home, not just as visitors, but as capable residents in a broader celestial neighborhood. Every field has its method for deciding what matters most. In planetary science, that method is something unusual, a structured conversation that unfolds across the entire community once every 10 years. It's called the Decadal Survey, and understanding it reveals more about how missions are chosen than any press release or budget justification ever will. The Decadal process is not fast and it is not simple. The National Academies convene panels of scientists, engineers, and policy experts who represent a broad cross-section of the field. Over the course of roughly 18 months, they read hundreds of white papers submitted by researchers around the world. These papers outline scientific questions, mission concepts, technology gaps, instrumentation needs, and opportunities for collaboration. Each one represents a small piece of the community's collective curiosity. I've spent years reading these documents, meeting the people who write them, and watching how they shape the direction of space exploration. What the Decadal Survey attempts is remarkably difficult, transforming thousands of individual scientific desires into a coherent set of priorities that NASA can realistically pursue. The process is both visionary and constrained. It sits at the intersection of what scientists want to know, what engineers believe is possible, and what federal budgets can support over the next decade. 3 tiers anchor the final recommendations. At the top are flagship missions. These are the largest missions NASA builds, complex, expensive, and designed to answer profound scientific questions. Flagship missions often cost as much as a major museum or a national research facility. Examples include Cassini, Curiosity, and Europa Clipper. They define an era. The Decadal Survey usually identifies only 1 or 2 such missions for the coming decade because each requires long-term political and financial stability. The next tier is the New Frontiers program, mid-size missions that target a specific list of scientifically compelling destinations. Past New Frontiers missions include OSIRIS-REx and Juno. These missions are ambitious but not open-ended. They follow a curated menu of eligible concepts that the Decadal Survey updates. At the base of the structure is NASA's Discovery program. Discovery missions are smaller PI-led projects, meaning the principal investigator carries significant authority. They are designed for innovation, for risk, and for breadth. Many of the most creative mission concepts come through discovery competitions because the cost limits encourage focused, clever solutions. Mars, Pathfinder, Dawn, and Lucy all emerge from this program. When the Decadal Survey makes recommendations, it considers this entire ecosystem. A flagship mission cannot dominate the budget to the point that discovery missions disappear. A surge in Mars spending cannot drain resources from outer planet exploration. A balanced program requires steady cadence, small missions for innovation, mid-sized missions for depth, and flagships for transformative leaps. The best current evidence from NASA's own program history shows that when any tier collapses, the entire scientific enterprise slows for years afterward. The debates inside a Decadal Survey can be intense but respectful. Planetary scientists are choosing between extraordinary possibilities: a return to Titan with a nuclear-powered rotorcraft, a mission to Neptune and Triton, a Venus lander capable of surviving hours in a furnace-like atmosphere, a sample return from a comet nucleus, or further steps toward Mars sample return. Each of these initiatives answers a different class of scientific question. Each requires unique technologies and decades of commitment. Because mission development timelines stretch so long, the Decadal Survey has to make decisions with incomplete information. Europa Clipper will not return its first data before the next survey must choose priorities. The same is true for Psyche, Dragonfly, and future Mars missions. The panel does its best by using the most reliable models and the most mature scientific understanding available at the moment, but inevitably some bets are made before the cards are fully visible. I often think of the Decadal Survey as a kind of societal mirror. It reveals what questions we are willing to wait 10 or 15 years to answer. It reveals how much risk we are willing to accept, how much infrastructure we intend to build, and how far into the solar system we want to extend our reach. For you, watching from a distance, it may look like a set of arcane decisions, but these documents shape the spacecraft you will see in the sky a decade from now. When NASA aligns its program with Decadal recommendations, and historically it almost always does, Congress gains a defensible roadmap for budgeting. Scientists gain a shared sense of direction. International partners can decide where they fit, and the public receives missions that reflect the consensus of an entire field rather than the preferences of a single administration. Every field has its method for deciding what matters most. In planetary science, that method is something unusual, a structured conversation that unfolds across the entire community once every 10 years. It's called the Decadal Survey, and understanding it reveals more about how missions are chosen than any press release or budget justification ever will. The Decadal process is not fast, and it is not simple. The national academies convene panels of scientists, engineers, and policy experts who represent a broad cross-section of the field. Over the course of roughly 18 months, they read hundreds of white papers submitted by researchers around the world. These papers outline scientific questions, mission concepts, technology gaps, instrumentation needs, and opportunities for collaboration. Each one represents a small piece of the community's collective curiosity. I've spent years reading these documents, meeting the people who write them, and watching how they shape the direction of space exploration. What the Decadal Survey attempts is remarkably difficult, transforming thousands of individual scientific desires into a coherent set of priorities that NASA can realistically pursue. The process is both visionary and constrained. It sits at the intersection of what scientists want to know, what engineers believe is possible, and what federal budgets can support over the next decade. 3 tiers anchor the final recommendations. At the top are flagship missions. These are the largest missions NASA builds, complex, expensive, and designed to answer profound scientific questions. Flagship missions often cost as much as a major museum or a national research facility. Examples include Cassini, Curiosity, and Europa Clipper. They define an era. The Decadal Survey usually identifies only 1 or 2 such missions for this coming decade because each requires long-term political and financial stability. The next tier is the New Frontiers program, mid-sized missions that target a specific list of scientifically compelling destinations. Past New Frontiers missions include OSIRIS, REx, and Juno. These missions are ambitious, but not open-ended. They follow a curated menu of eligible concepts that the Decadal Survey updates. At the base of the structure is NASA's Discovery program. Discovery missions are smaller, PI-led projects, meaning the principal investigator carries significant authority. They are designed for innovation, for risk, and for breadth. Many of the most creative mission concepts come through discovery competitions because the cost limits encourage focused, clever solutions. Mars Pathfinder, Dawn, and Lucy all emerge from this program. When the Decadal Survey makes recommendations, it considers this entire ecosystem. A flagship mission cannot dominate the budget to the point that discovery missions disappear. A surge in Mars spending cannot drain resources from outer planet exploration. A balanced program requires steady cadence, small missions for innovation, mid-sized missions for depth, and flagships for transformative leaps. The best current evidence from NASA's own program history shows that when any tier collapses, the entire scientific enterprise slows for years afterward. The debates inside a Decadal Survey can be intense but respectful. Planetary scientists are choosing between extraordinary possibilities: a return to Titan with a nuclear-powered rotorcraft, a mission to Neptune and Triton, a Venus lander capable of surviving hours in a furnace-like atmosphere, a sample return from a comet nucleus, or further steps toward Mars sample return. Each of these initiatives answers a different class of scientific question. Each requires unique technologies and decades of commitment. Because mission development timelines stretch so long, the Decadal Survey has to make decisions with incomplete information. Europa Clipper will not return its first data before the next survey must choose priorities. The same is true for Psyche, Dragonfly, and future Mars missions. The panel does its best by using the most reliable models and the most mature scientific understanding available at the moment, but inevitably some bets are made before the cards are fully visible. I often think of the Decadal Survey as a kind of societal mirror. It reveals what questions we are willing to wait 10 or 15 years to answer. It reveals how much risk we are willing to accept, how much infrastructure we intend to build, and how far into the solar system we want to extend our reach. For you, watching from a distance, it may look like a set of arcane decisions, but these documents shape the spacecraft you will see in the sky a decade from now. When NASA aligns its program with decadal recommendations, and historically it almost always does, Congress gains a defensible roadmap for budgeting. Scientists gain a shared sense of direction. International partners can decide where they fit, and the public receives missions that reflect the consensus of an entire field rather than the preferences of a single administration. Behind all of this lies a simple truth. Exploration happens slowly. A flagship mission selected today may not launch until the early or mid-2030s. The first published scientific results might arrive years after that. And yet, every decadal cycle restarts the conversation, giving scientists a moment to ask themselves which deep questions deserve priority. Thinking this way creates a certain calm perspective. You begin to see exploration not as a sequence of isolated missions, but as a long, deliberate unfolding of ideas chosen by a community that understands both the limits of the possible and the value of patience. In many ways, the Decadal Survey is the quiet engine of planetary science, slow, steady, and profoundly influential. Our path from here turns toward the tools that make these priorities real, the experiments, demonstrations, and new technologies that allow spacecraft to do more than ever before. That story begins with a small, reflective sail drifting through sunlight. Space exploration moves at a pace that rarely matches the rhythms of daily life. Most of what you and I see, an image from a distant moon, a successful landing, a fresh set of spectral data, represents events years or even decades in the making. I often describe exploration as a conversation across time. Engineers speak through designs that outlive their tenures. Scientists pose questions whose answers may arrive after they retire. And the public, through attention and support, shapes which questions even get asked. A typical planetary mission takes roughly 1 decade from formal start to launch. That is just the engineering arc. Add the years of data collection after arrival at its destination, the scientific analysis that follows, and the publication cycles that refine those results. What you get is a continuous timeline stretching 15 to 20 years between an idea and its fully realized scientific return. This slow accumulation of progress can feel distant from the rapid news cycle we live in, yet it is the natural scale of exploration. Planetary science, like geology, unfolds across long spans. In that context, citizens are not observers standing outside the process. They are part of the system itself. At the Planetary Society, I've watched thousands of people take small actions that create measurable effects in Washington. When budgets are being negotiated, or when a program is on the verge of cancellation, a wave of constituent messages can shift the level of attention inside a congressional office. Staffers who hear from 10 people in a single day about a space issue will notice. If they hear from 50, they will ask their committee specialists what is happening. If they hear from 100, their boss will take the meeting. These moments do not resemble the dramatic scenes people might imagine. No protests on the Capitol steps, no sweeping speeches. Instead, advocacy works like a pulse, a brief rise in public attention that reminds policymakers that someone beyond the Beltway cares about the future of exploration. This works because space is not a polarized issue. Unlike many areas of public life, it does not fall neatly along ideological divides. That means smaller groups of motivated citizens can have disproportionate influence. In practice, exploration advances because people choose to care. One example of this relationship between citizens and policy is the Congressional Planetary Science Caucus. It exists today because several members of Congress recognize the need for a structured forum dedicated to exploration, and because the Planetary Society worked behind the scenes to make the idea viable. Our role was not to dictate priorities. It was to provide information, answer questions, and connect interested lawmakers with a community of advocates ready to support science. When the caucus launched, it created a durable point of focus inside the legislature, an institutional foothold for planetary science. These successes never belong to a single organization. They are cumulative results of many people taking steady, coordinated steps. Advocacy depends on 3 components: a clear goal, a simple message, and consistent groundwork. Before asking thousands of members to write or call Congress, my colleagues and I spend months preparing. We brief offices, explain the stakes, check the evolving language of the budget, and build relationships so that when a surge of messages arrives, they land on receptive ground. Grassroots advocacy works best when it supplements careful, patient preparation. A single image from another world can feel effortless. It appears on your screen without strain. A stretch of Martian dust, a shadow crossing Saturn's rings, the faint glow of a distant moon. But after spending this hour with you, I suspect the picture looks different now. Not less beautiful, just more complete. Behind every frame is a chain of choices made by thousands of people across decades. Scientists refining questions, engineers shaping hardware, policymakers debating budgets, citizens nudging attention toward exploration. The image is the final moment of a long, quiet negotiation between curiosity and time, understanding that machinery does something important. It makes exploration feel more human. You begin to notice the subtle weight of each decision, how a few sentences written into a budget one year can lead to a spacecraft gliding past an icy moon 15 years later. You see how consistency, not spectacle, keeps a program alive. And you realize that the most astonishing discoveries often rest on decisions that felt ordinary when they were made. Thank you for staying with me through a topic that rarely moves quickly and never chases drama. It means something to spend an hour on the hidden structure that makes the exploration possible. If you ever want to go deeper, there are accessible summaries of the decadal surveys, public documents on the NASA budget, and countless mission archives filled with stories that rarely reach the headlines. You can join the Planetary Society if you like, but you don't need to. Curiosity alone has its own influence. I'll leave you with one last image. Imagine a small spacecraft drifting through the dim light beyond Earth, guided by signals from a civilization still learning how to cooperate with itself. Every maneuver it makes reflects a choice someone cared enough to fight for, and in a quiet way, that connection includes you.